Hi, in this video we are going to talk about Wgans, and the motto for Wgan is that the standard GAN is well known for being delicate and unstable. So let's see how this Wgan solves the problem of unstable learning and all the other challenges which regular GAN faces. First of all, let's see what are the challenges. One of the first challenge that regular GAN faces is the lack of matrix. This means that we don't have a useful loss function or metric that correlate with the generated image quality. So as you can see in the left graph, we have generator loss and discriminator loss, and with increasing number of epochs our discriminator loss is around 0.5. It's like flipping the coin, either an image is real or it is fake. So our discriminator loss is around 0.5, while our generator loss is between 1.5 and 0.75. So this is the common scenario which you will face when training the GAN. You don't have a very meaningful matrix. And on the right side we have the image from the original GAN paper, and as you can see, with increasing number of epochs our image quality is increasing, but still there is no increase in the accuracy of the model. So there is no useful metric that correlate with the quality of the image. The second challenge in GAN is the mode collapse. And the mode collapse is a problem that occurs when the generator learns to map several different input Z values or random noise to the same output point. So on the left side of this image, as you can see, we have our training data distribution. We have different handwritten digits, but on the right side, once our model is trained, it is like just generating 0 and 1s. It has learned how to convert that random noise into just two digits, either 0 or 1. So this is called the mode collapse, and you can learn more about this mode collapse by going to this URL. It's a LinkedIn blog, so make sure to check it out. It's quite useful. Then the third challenge which regular GAN faces is the convergence failure. Now what is convergence failure? It means that generator get stuck in some bad local minima and start generating nonsensical images, while discriminator keeps improving and reaches accuracy of nearly 100%, or the loss of discriminator reaches to 0. And the reason for this is that because the generator part of the GAN is producing nonsensical images, that's why it is very easy for the discriminator to classify between a real image and a generated image. So on the left side we have plots, and in these plots you can clearly see that the loss of the generator is increasing. So this green line represents the loss of the generator, while this orange line represents the loss of the discriminator, and the loss of the discriminator is decreasing epoch by epoch, and it reaches to 0. This kind of graph shows that we have convergence problem, and similarly right below we have the accuracy plot, and here as you can see the accuracy of our discriminator is increasing and it has reached to 1 or 100%, while on the left side upon inspection we can see that the generator is producing nonsensical images. It's like just noise. There is nothing. We have a black dark spot right in the center of each image, but still it doesn't make sense. So these are three main challenges that a regular GAN faces, and because of these three main challenges we have further other challenges like vanishing gradients, etc. So in order to solve these problems, the WGAN paper, which was proposed in 2017, introduces a new loss function called the earth mover's distance, which measures the effort needed to transform one distribution into another distribution. So now you will be thinking that, okay, why do we need this earth mover's distance loss function when we have loss functions like callback, which measures the distance between two probability distributions? So the simple answer to this question is that earth mover's distance loss function is more robust and more powerful. And the reason is that if you see this plot, this is one pair of distribution and this is another pair of distribution. And in the left pair, as you can see, that Wasserstein distance or Earth mover distance is 2.0 and the Kell divergence distance is 0.89. But if you see to this right side pair, here the Earth mover distance is 0 0.5 and the Kell divergence is still 0.89. So in both cases, the Kell divergence loss is same, but the Wasserstein distance or loss is greater in one case and smaller in other case. And the reason for this is that if you look to this blue distribution, in order to map this blue distribution on this red one, our model needs to put a lot of effort because we have to move this big blue bar to the left side. And in case of this right pair, we can see that we need to put very less amount of effort in order to move this blue bar to the left side, and this effort is depicted in these values of Wasserstein distance. So in this case we need a lot of effort, that's why the distance is higher, and on the right side we need to put little effort, that's why the loss is small. And I think this is going to clear a lot of confusions regarding earth movers distance and Kell divergence loss function. So our ultimate goal in this WGAN is to make the distribution of generated image as close as possible to the distribution of real images. So this is our ultimate goal. Now if you read the original paper, they actually compared the Jensen Shannon divergence loss function with Wasserstein distance loss function. So in this graph, the x-axis represents the parameters which control how different the two distributions are. So it's like if you increase this t, the difference between two distribution will be high, and if you decrease this value, the difference between two distributions will be low. And on the y-axis we have the distance measure. So in this plot, the blue line represents our Jensen Shannon divergence loss function, which is another variant of Kullback divergence loss function, but it is better than Kullback. So that's why they have compared Jensen Shannon with the Wasserstein. So the blue line represents my Jensen Shannon divergence, and this dotted black line represents my Wasserstein loss function. And you can clearly see that JS divergence does not provide useful gradients for training when the distributions are not very similar. So it makes the training process of GAN difficult. When they are same, like in this case, so here we have this portion, we have some useful gradients, but when the difference is high, then our JS divergence is just a flat line, and in these cases we don't have any useful gradients. On the other hand, if you see the black lines, it represents the Wasserstein distance, and it increases linearly as the difference between two distribution increases, which shows that it provides consistent and useful gradients for training regardless of how similar or different distributions are. So that's why the Wasserstein loss function or earth mover loss function is far better than Jensen Shannon or Kell divergence loss function. Now there are some other features of WGAN as well, and one of them is that WGAN does not require maintaining a careful balance in training of discriminator and generator. So in standard GAN we have to make sure that our generator and discriminator is being trained equally, but this is not the case, and in fact we will see that we want our discriminator to be bit better than our generator, which help us train the generator easily. The second feature of WGAN is that it doesn't require us to carefully design the network architecture either. So in standard GAN, if we do not carefully design this network architecture, our generator gets stuck into some local minima. And finally, the mode collapse phenomena is also drastically reduced in WGAN. Now let's talk about the discriminator objective. So in standard GAN, the discriminator job is to classify images as either real or fake. This means that it outputs a probability between 0 and 1, where 1 means that image is real and 0 means it is fake. So the goal is to maximize the probability for real images. So for real image, we want that the model should output a value or probability which should be close to 1. And in case of fake image, we want it to minimize. This means that the probability should be close to 0. But in case of WGANs, the discriminator job is no longer to classify the image, but rather it outputs a score for each image, and that's why the discriminator in WGAN is called critic. And instead of outputting a probability, it outputs a score for each image. And the objective is to maximize that score for real image and minimize that score for fake image, and this score reflects how real the critic believes an image is. So the architecture of WGAN is very similar to standard GAN, but instead of outputting probabilities, it is going to output score, and there is no sigmoid or any other activation function on the last layer. So the critic prediction is unbounded and can be very large positive and negative values, and this gives rise to another concept which was introduced in the original WGAN paper, and that is Lipschitz constraint. So what does this Lipschitz constant mean? During training of WGAN, we want that neural network should behave smoothly without any sudden jumps in its output. And we might get these sudden jumps because we don't have any activation function on the final output of the critic. And in order to avoid these sudden jumps, according to the original paper, the neural network must satisfy a mathematical condition called the Lipschitz constant. And obviously, we are not going to dig into maths in this video, but all it does is that it ensures that the changes in the output of the network are controlled and smooth. So mathematically, they will look something like this. If the output of the critic is d of x, then the one Lipschitz condition should satisfy the following inequality, and that is, if x1 and x2 are my two images, then the absolute difference between their critic score should be less than or equals to the average of their absolute pixel-wise difference. So this n represents the number of pixels and x1I is my ith pixel. And in order to enforce this Lipschitz constant in critic, in the WGAN paper, author introduced that weight clipping method, which means that weights are clipped to the range of negative 0.01 and positive 0.01. So these are the values which were introduced in the original paper. But with this weight clipping, we have some potential problems. The first problem is that if the range is large, then training the critic to reach the optimality is harder. And the second problem is that if it is very small, then it can lead to vanishing gradient problems. So these are two potential issues which were highlighted in the main paper, and that's why now we need an alternative method to apply one Lipschitz constant without using that weight clipping method. And this problem was solved in this paper, Improved Training of Wasserstein GAN, and they introduced the technique called gradient clipping to enforce this one Lipschitz constant in WGANs. So in the next video, we are going to talk about this gradient penalty method, and I'll see you there. Bye bye.